Lesson 1. Types of conducted noise. Differential mode and common mode. Starting with differential mode noise. Differential mode noise is noise between two conductors. It's often from switching devices within the circuit. If we look at the animation here on the right side, we can see how the differential mode noise flows from the positive source to the negative source, like this. Common mode noise, on the other hand, is noise that flows in phase on both lines together through parasitic capacitance to chassis, just like we see in the animation here. Common mode noise is often driven by fast dv/dt nodes through heat sinks, shields, transformer interwinding caps. It's also caused by coupling from external fields, like inductive coupling or capacitive coupling, caused from sources that are outside the device that we are concerned with. The intensity of the common mode noise that's generated is proportional to the parasitic capacitance multiplied by dv/dt, or the slew rate. That means the highest the slew rate on a switching node, the higher the common mode noise will be generated. Also, the higher the parasitic capacitance that is between the switching node and ground/earth, the more common mode noise will also be generated. To give a better idea on how noise could be generated through coupling, I've put together this table. So if you recall from our previous module, we've talked about the different modes of coupling that we can see. So we talked about capacitive, inductive, and conductive coupling. Now, I have to say that when it comes to capacitive and inductive coupling, or radiated coupling in general, these types of couplings will cause or will lead to usually more common mode noise than differential mode noise. Because in most cases, what happens is that they couple with the same intensity on both lines, the positive and the negative, with respect to ground. Take, for example, a long cable near an inverter. That cable, if it generates an electric field, what will happen is that both lines that are inside the inverter will see the same voltage. That will cause common mode noise with respect to ground. On the other side, or on the other hand, take asymmetric routing, which basically means that we could have one line closer to the source of the electric field than the other. In that case, what we'll have differential mode noise, because one line is seeing a more intense electric field than the other. Now, when it comes to magnetic field, we can take the transformer leakage field as an example. The transformer leakage field is basically magnetic field and can cause common mode or differential mode noise depending on how it's coupling on the adjacent conductors or loops. And the last one that I have on my list is conduction via ground path. Conduction via ground path will always cause common mode noise, and that is what we also know as ground bounce. Going back to a topic that I touched upon in the previous module, this is a plot that covers how common mode and differential mode noise become more or less prominent as frequency increases. So if we look at differential mode noise, we can see that in the frequencies basically below 1 MHz, it is much more prominent, and it starts to get less and less prominent as the frequency increases. On the other hand, common mode noise, it is much less prominent below 1 MHz, and as frequency increases, it starts to get more and more prominent. In the next lesson, we're going to be talking about how we measure EMI using a listen. Stay tuned.